Alright, so welcome to recap lecture number 3, the face-to-face one, if I'm not mistaken, and this is the fourth, including the exclusive huge lecture, the online exclusive one. Alright, so we recapped a little bit the direct map caching and the mechanism of it, and the fact that everything is mapped to exactly one location in the cache, and in order to get that particular location we need to have the size of the cache and then the full size, the address of the main memory. And by using the modulus operator, we are able to get the address within the cache of the block that we're looking for in the main memory. So using both the addresses of main memory and then the size of the cache, we're able to operate the modulus here in order to know what is the index, or what is the address for now, of that particular block within the cache. And we've noticed that those blocks, for instance the gray ones, they have something in common, and they share this particular block, and we can see that's repetitive here. The 001, 001, it keeps on repeating itself in each of the blocks, hence it makes sense to put it all over there. Another way to find out, it's all about the y lowest bits, y being the size of the to the power of the size of the cache. So if you have a next block cache, so we're going to use the y lowest bits as the block address within the cache. Alright, and we said that we needed a way in order to find out, because all the words are sharing blocks. Words doesn't really matter for now. So let's assume that a block size is a word in this case. So we needed a way to differentiate between the different words that we have in the particular block. And one idea is, instead of using extra overhead, why not use something that changes between those gray blocks, for instance. And we can notice that the two first bits here are the ones that constantly change, hence we can use them as a differentiator between the different words that might be in that particular word here or block. Alright, so this is why we divided our main memory address, into an index and some tag. So the index is nothing but the address within the cache, and then the tag is the thing that will help in differentiating between the different words that might share the same block within the cache, right? And then we have the data, and we said the data could be virtually any size, but then again, most probably in most of the architectures it would be 32 bits, so 4 bytes. But this depends from it's a case-to-case base, so generally speaking we're gonna stick to 32 bits for now. Right, and instead of wasting time, because again time is performance, looking in an index whether the tag corresponds to the word we're looking for or not, well, we needed to go faster because we want to improve our performance. So doing away with the fact that we need to dig if nothing is inside the cache yet. And this is where we had a lot of fun in the class trying to guess in which cases, so what kind of scenarios will lead us to that. One of the easiest scenarios is the fact that we just turn on our computer, and because cache is made out of RAM, so basically nothing will be there. So it's not even worth it to go look to dig out the tag and try to compare it, because at the very beginning there's nothing, and we know that. So maybe it could be interesting to have some kind of valid bit. It's like a flag, in order to say that we have something there, so it's worth it to go ahead and compare, or we have nothing at all, and then it's not even worth it, so we don't waste any time doing that. So that I made someone do the exercise live with everyone. So try to guess first off the size of the cache using just the information that we have here, and apparently a lot of your colleagues guessed it correctly, that because we're using 2 bits here as an index, so most probably the size of the cache is just 4 blocks, and it is true. So with 2 bits we can have 4 different locations. They go from 0 to 3. And then because we have no info about the tag, so basically we cannot know how many addresses we have in main memory or the size of the main memory, but we're gonna get to that soon. And here you can notice that all the valid bits here for each blocks are 0, so most probably this is the very beginning where, and you can see that the cache is empty. So yeah, so all the valid bits here are set to negative, to false. And the idea is, naturally, because the cache is empty, so basically when we're going to go to the main memory address 11010, will systematically have a miss. However, using this information we can guess the size of the main memory now, and because we're using 5 bits in order to address the main memory, so basically the size of the main memory would be 2 to the power of 5, with addresses going from 0 to 2 to the power of 5 minus 1. And the whole idea here is we're using 2 bits for the index, hence in order to be able to compare the words, well, we're going to be using 3 bits for the tag. So yeah, definitely we'll have a miss here. However, the question is, where exactly, in which line should we witness the miss, and where are we going to load our word from main memory into the cache? So using the last 2 bits here, so it should be here, and this is exactly it. So the next time I'm trying to address the main memory with that particular address, well, I'm gonna find it now in my cache, and I will witness a hit instead of a miss this time. And then, in order to make sure that everyone got that, I ask students to try it with this address, for instance. So we're doing that, right? So what would be it? So what would happen? What is the mechanism that happens here? So we're gonna go for the index 10. Apparently we had a valid, so we're gonna go ahead and compare the tags. And this tag that we have here is 110, whether here we have 111 here. So basically this would be another miss, and then we're gonna kick out that one and replace it with that word, with whatever data is represented in that address. So this is the new data. Alright. One of the main things that I tried to explain in the last face-to-face lecture is the fact that out there in most of the architectures, well, there's a constraint that is called the memory alignment restriction, right? And the whole idea is to organize the memory in 4 bytes of words. So each line in the memory is made out of 4 bytes or 32 bits. Hence, on each line we will be 4 bytes away from the second one, from the 8 bytes away from the third one, etc. So between 2 lines here we'll always be at 4 bytes away. And let me see that. Let me explain that for a moment. So this is the address of word number 0. So here's word number 0, right? So the word address of word number 0 will be naturally 0. The word address of word number 1 would be naturally 1, because we are 1 word away, and a word is made out of 32 bits, and this is what we're sticking to now, for now. Well, word number 2 will have word address number 2, and etc. The whole idea now is, instead of using word addressing, I want to go ahead and use byte addressing, and this is what usually people do, and the architecture are based on byte addressing. So if a word is made out of 4 bytes, so let's see, let's assume that this is B0, B1. I'm just assuming, it could be the other way around as well, B2 and B3, and then this will be B4, B5, etc., etc. So if I'm looking for my bytes 0 here, or the other way around, doesn't really matter, right? So this is at byte address number 0. If I'm looking for my byte number 1 here, this is at byte number 1. byte address number 1, etc. for exactly for byte number 3 and byte number 2 and byte number 3. Now all these bytes are in word 0, so they belong to the address with the word, to the word with address 0. Now for the word with address number 1, so word address number 1, well, it contains byte 4, 5, 6, and 7. So you can notice that the very first byte here is byte number 4. Hence, see, the byte address of word number 1 is 4. Fair enough? So the byte address of word number 0 is 0. For the byte address of word number 1 is 4. The byte address of word number 2 would be 8, etc. And you can see the pattern here, and it's the same thing. Now the question is, what if I wanted to reach one of the bytes within the word? Well, the beauty of it, if you're having the byte address of the word, all we have to do is apply some kind of offset to it. Fair enough, in a way or another. So if I'm going, let's say, to word number 0, so with byte number 0, and I'm having an offset of 2, so I'm gonna add 0 to 2, and I'm gonna end up with byte number 2 if I'm looking for byte number 2 within the word. Alright, fair enough. This is if I'm looking for bytes. Now the question is, if I'm looking for words, so systematically I'm gonna take the first 4 bytes at the byte address that is, that we're having for the word. So with word number 0, for instance, so byte address number 0, systematically the consecutive bytes starting B0 will be taken into consideration. So I'll take B0, B1, B2, B3. Same is for word number 1. So its byte address is 4, hence a word at 32 bits, so 4 bytes. So I'm going to take 4 bytes starting with byte number 4, 4 bytes, byte number 4, byte number 5, byte number 6, and byte number 7. I'm good, etc., etc. Fair enough? So word addressing and byte addressing, and we're going to stick to byte addressing, and byte addressing are always 4 words away, 4 bytes away, 4 bytes away. Each word is 4 bytes away from from its neighbor. Alright, so this is an implementation mechanism, and we have noticed something, and I want you to keep that in mind. So in byte offset within the word, a word is made out of 4 bytes, so a byte offset within the word needs to have a number of bits that will be representing 4 things, so 4 bytes. So in order to get to 0, 1, 2, 3, right, how many bits are needed in order to represent a number, the number 4? Well, 2 bits are needed. Hence, we can notice that we've reserved 2 bits for the byte offset within the word. Fair enough? So let's see here. So this is in NAND, and I'm ending whatever the tag that I have here with the comparison of the tag. So the tag that I'm having, I'm comparing it to the tag that is present in the cache, and then the result of that comparison is ended with a valid bit. So if I should have a valid bit set to 1, and the tag should be equal to the tag that I'm looking for, the memory address, main memory address. If it's the case, then I'm gonna get a hit. If it's not the case, if there's no valid bit or the tag is different, well, I'm gonna get a miss. Fair enough. Where's my laser pointer real quick? Alright. And then you have the 32 bits of data as we said, and then we have the index. And you can guess the index here, is it a byte addressing or is it word addressing? What does it feel like? Well, you can notice that it's 0, 1, 2, 3, so it feels like it's word addressing because we're talking about word number 1, word number 0, word number 1, word number 3, etc., etc., which is, by the way, 4 bytes away from each other. And hence, in order to reach the byte within the word, well, we're using the 2 bits in order to offset whatever things we need within that word. Fair enough? Awesome. So here we can notice the index, how many bits are used to the index. It feels like we have 10 kilobytes here. Yeah, so 1000 10 to the 2 to the power of 10, that's correct. So 2 to the power of 10, so 10 kilobytes here. And So that's it. We're using 10 bits, for the address of the cache. Fair enough? And we're good. So we have 10,024 blocks here. So we have 10 bits in order to reach whatever block we want within the cache, right? And this is based, of course, on the main memory address. So this is the index part of the main memory address. So theoretically, if I'm using 10 bits out of the 32-bit address as an index, well, I'm left with 32 minus 10, so 22. How come I have 20 here? For the tag, so to be able to compare the words, well, I have 20 for the simple reason is I'm using 2 bits, remember, for the byte offset within a word. So I need to take out the 2 bits here from the whole address, so I'm left actually with, instead of 32, I'm left with 30 bits, out of which I'm taking 10 for the index, and then I'm left with 20 bits in order to get to the tag. Fair enough? You can read that, and of course the byte offset here is because of the memory alignment restriction that I talked to you earlier in the previous slide. Alright, so here we tried to have a huge debate about the impact of whether memory have some kind of impact on performance, and a lot of the students that I really enjoyed debating with, they said naturally, because they heard it so many times in the OS and the C8 till now, that the hardware components are usually slower than the CPU, and therefore they should have, and memory is one of the hardware components, so there should be some kind of impact on that. So we tried to figure it out, and before doing that, we tried to reminisce on how its performance is measured, taking into consideration the CPU and the execution. And the thing is, we ended with saying that the CPU time takes into consideration, well, how many instructions do I have in order to be able to compare computers. For instance, we need to run the same program so we can compare bananas with bananas and apples with apples and not apples with bananas. So basically, if we're going to take a 10 instruction program, for instance, and figure out how many cycles are needed per instruction within that program, and they could be different. And then we needed to know, well, how fast is the cycle? So what is the size of this clock cycle? And this is determined by the clock frequency that we're using within our architecture. So yeah, it's the instructions, how many cycles per instructions, the number of instructions, and how many cycles per instructions, and the cycle speed, quote unquote. Hence the length of a cycle, and this is determined by the frequency of the CPU. So yeah, today we added, last time we added in the face-to-face lecture, how much the memory is stalling. So how many, stalling, stretching, delaying, how many clock cycles are being eaten by the memory. So we figured out that maybe not all instructions need the memory, hence we're gonna take into consideration only the instructions that will deal with the memory. So anything that I'll be reading from the memory or writing to the memory, fair enough. And the other instructions, maybe some mathematical and logical instruction, they will happen without the need of the memory. Hence, there are no memory stalls whenever we don't deal with the memory. All right, and we try to to break down the memory stalls into different things. So yeah, so everything that is related to cache misses, and we're focusing on the cache here. So naturally, if I'm fetching something from the main memory, I'm gonna look for it before in the cache, and this is the whole point of the cache, because it should speed things up. However, if I'm not finding what I'm looking for in the cache, what would happen? I'll witness a miss, and the more misses I have, the higher the miss rate, the more time I will lose. And the whole idea is to try and figure out what would happen, what would cause a miss. Well, we can see it into two things. It's either I'm trying to read something and it's not there, or I'm trying to write something to a variable and it's not there. So this is where, again, I tried with the students to to figure out what are the read stall cycles and the write stall cycles, and we started with the easy part, which is the read stall cycles. And it all goes down to that. So how many instructions are trying to read something from the memory? So let's imagine that we have 3 instructions that are reading something out of the program, right? 3 instructions with reading something from memory, and we're gonna go and figure out how many are missing and how many are not missing. So basically the miss rate of the reads, and then how much time we'll be losing whenever we have a miss. And this is what we called in the previous lecture the read miss penalty. All right. Yeah, so here's where I ask someone to try to, using what we've learned till now, to write some kind of equivalence. And this is what I usually do in the exams, by the way. I give you something, and then you're gonna use your engineering skills in order to give me something else. And the whole idea is the read stall cycles. Well, I want to have the write stall cycles using the same, plus or minus, using the same approach here. So as the good engineers we are, well, we, especially software engineers and coders, computer programmers, well, if you find something in the internet, all you have to do in order to reuse it or use it or integrate it in our project or the thing that you're trying to make, well, all we have to do is select it, copy it, and then paste it and make the proper adjustments. And sometimes we just forget to make the proper adjustments. However, all right, so as the good engineers that we are, so we're gonna copy paste that one and remove reads and replace them with writes, and this should be the solution. However, that's good, but not good enough. So let's think for a second, what would be different from the reads and the writes? What should we do when it comes to the writes? So this is where I need you to think about it from an engineering point of view. So reading, what would be the difference between reading and writing too? Which is easier? Naturally, you're gonna say that reading is easier because we're gonna go and see something in the cache. If it's not there, well, all we have to do is go ahead and take a copy of it and put it in the cache and then get, and use it in this view, whatever. What about the writes now? Well, the writes, they are kind of special because if I want to write to a variable that is not in the cache, let me think about it for a second. Here's a pen. So let's say I want to change the value of variable a, right? So basically, variable a in main memory is 0, and variable a is not present in the cache. And I want to write something, one of the instructions saying that write 2 to a. So I'm going to go and check the cache. It's not there. So in a way or another, again, in a way or another, might not be the exact implementation of it, but I need to get my a here in the cache, right? So I did witness a write miss here. Give it the value of 2 and do something else. Well, unlike a read, I need to make sure that whatever I updated the value, the value that I updated the variable with, it should be consistent in the main memory as well. So I need to, instead of having 0 here, I need a way to have 2. So I need to copy whatever I have here and put it back in the main memory, right? This is an example of an implementation. So this is how we witnessed a miss here, and then we've written to the main memory. So what can you notice here? Well, it's going to take me some time to do that as well. So I don't want to pay the price, especially because the main memory is slower, even slower than the cache. Alright, so what I'm gonna do is I'm gonna use some buffers. So the idea here is we're gonna have some buffers, in order to be able to have some consistency with the main memory as well. Usually, in order to make our life easier, we consider that the number of writes is, and this is a general approach. Well, if you have it in your exam or somewhere on your quiz, if we don't precise that, you can consider that the number of reads are usually higher than the number of writes when it's come to the memory, usually. Hence, we can forget about the writes, all right? And we can get to that. We can. However, if in a way or another the writes are mentioned in the exercise or in real life later on, because in real life you're gonna take into consideration that. So basically, you need to remember this particular set, a part of the equation. Alright, so we went from something that is extremely fast, which is the direct map caching, and then I asked students to imagine something that is a different implementation for a cache. And some of them said that the problem with the direct map caching is if I'm looking for something, of course it's very fast because I'm gonna look for it only in one block only here. If it's there, it's there. If it's not there, I'm done. However, we can notice that maybe for some reason the whole cache will be left empty, the whole cache but one block, the one that for some unlucky scenario here, all the words are in that particular block. So we can notice that we didn't have any flexibility with the direct map caching, and this is where the associative cache comes in handy. And the idea of an associative cache is, instead of just focusing on one block, well, we can use any block within the cache. What is the drawback of that particular implementation? Well, you can notice that unlike the direct map caching, instead of looking only in one block to find the word I'm looking for, well, now I have to look in all the blocks here because my word could be anywhere, right? Hence, I'm gonna lose time looking for it compared to the direct map caching. So when it comes to engineering, it's all about trade-offs. So what you see, the best of this world and the best of that world, and we try to to adapt to a situation or things that are needed. The question is, now that we've seen the direct map cache and the associative cache, well, I'm gonna create something that is the best of the two worlds. So I'm gonna try make a baby out of the two approaches, something that is in between the fully associative and the direct map caching. Well, I want to offer the flexibility of associativity here with the speed of direct map cache. A solution would be the set associative cache. So here you can notice that I'm using sets instead of blocks now, and each set could be made out of more than one block. Fair enough? So it's the exact same principle of the direct map caching, but instead of using blocks, we're using sets now. So where's my pointer? So here we have sets. We have an 8 block cache, for example. However, it's divided into 4 sets. So each block could be in any of in one of those sets now. So let's imagine that block number 0 of main memory, well, should always be in set number 0. However, within that set that is made out of 2 blocks, it could be anywhere in those 2 blocks. So I have the flexibility of choosing the block within the set to put my word in. However, I don't have any flexibility. It should always be the set. Hence, it's faster because all I have to do is look within that set. If it's in that set, anywhere in any block of that set, I'm good to go. If not, well, I'm not going to look in the other sets because it's not meant to happen there. And this is why we use the same operation than direct operator than the compared to the direct map caching. However, instead of using blocks, we're using sets. Fair enough? And to give some naming for it, so a fixed number of location using sets, at least 2, because with one, what would happen if we have 1 block per set? Well, we are back to the direct map cache. So n-way set associative cache. N-way means that we're having n blocks per set. Fair enough? So what would be the name of that particular cache here? Well, we're having 2 blocks inside a set, 1 2 1 2 1 2, right? So 2 blocks for a set. So this is a 2-way set associative cache here, this example. All right. So uniquely to a set, and then within that set, it could be anywhere in the blocks. If we're having a 4-way associative cache, for instance, well, it could be anywhere. It could be within the 4 blocks that belong to one particular set, etc., etc. All right, and these are the cons and pros, and we said in a way or not, we figured out that the pros of associative is the flexibility, the cons is the speed of the time that we'll be losing in order to find a block. So the more associativity we have, the more flexibility. However, the more time it will take us in order to find a word. And we can see here the different things that we've seen till now. So one way, each block is dedicated to word, a two-way. We have two words, two places for one set. So this could be shared with two words. So maybe it will help us minimize the miss rate here. However, it takes us time to find out. Here we can minimize even more the miss rate, because you can notice that we can fit 4 words, up to 4 words within a set. However, we need to look for the word, etc. Then we don't have many options in set to fit words, so it's always a trade-off. And here with a full associative cache, what would happen? So a word could be anywhere, but then again we have to travel all inside all the cache in order to find the word or not, right? Compared to that one, this one no flexibility, full speed. This one is a lot of flexibility, fully flexible with extremely slow. Alright, so yeah, so if I'm sharing the blocks and I want to kick out a block, so let's take the full associative cache for instance. Yeah, let's do that. Let's have fun with that. Right, so I'm having a 4 block fully associative cache. So no sets, nothing at all. I'm having 4 things here, and I'm putting word number 1, word number 5, word number 7, and word number 929. Allez, on s'en fiche. And then so if I'm looking for word number 7, well, virtually it could be anywhere. So the whole idea is to go ahead and try to get it, to know which one. I'm gonna go through the whole cache in order to find it. So imagine that now my cache is full and I'm looking for word number 8. So basically I need to kick out one of the words that are in my cache and replace it with word number 8. So which one should I replace? I was extremely happy with the proposals of the students in the face-to-face lecture, and some of them told me that the oldest one should be kicked out. So in another word, the least recently used one should be out. So imagine that I used this one like 4 instructions away, and that one is 1 instruction or 2 instruction or 3 instructions. So basically it makes sense, because of the temporal locality. So I'm going to replace that with word number 8, right? So this means what? I mean, if I want to implement it from an engineering point of view, and you guys are engineers, so think about it. How would I able to know which one is the oldest? So the least recently used, well, I need to have some kind of timestamp. I want to be a real engineer, so I'm going to be very lazy. I need to find another way to replace the blocks. So the most laziest one, what would it be? Well, the laziest one is just, and this is always the case, go random. So here all I have to do is randomly choose one of the words, kick it out, and use it. Is it the most efficient one? Nope. Is it the easiest to implement? Yes. Right, so random or least recently used. And this is where we stopped with the memory, and then I asked people to go ahead and use their favorite search engine to find different block replacement mechanisms. Right, so I introduced what's coming next. So we wanted to talk about ISA, and as an example of an ISA, I'm gonna use the MIPS. And then I wanted to make sure that you understand now, as technical engineers, now you should see the difference between an ISA and implementation. So another name, ISA is short for instruction set architecture. I talked about it in the first video. And then we have something that we call the microarchitecture, or the implementation of an ISA. And one of the examples that we've seen in the first video was the fact that we're using a different, physically, one memory or 2 memories in order to store the instructions and data, and then we call them with different names. I'm not going to talk about them now. You can refer to the first video. Alright, so now we're done with the storage unit. We're going to tackle the stored programmed concepts of what is used by the CPU. So everything is stored in the memory. Well, I'm going to get my instructions and the things that I need from the memory in order to execute them. So I get them from here, right, and I execute them here. So yeah, because a meme is never forgotten, so basically you need to understand that the language of the CPU is the ISA. And I asked students within the class if all CPUs speak the same ISA out there, so all manufacturers implemented the same ISA, and they've brilliantly answered that nope. We have different ISAs for different types of CPU, or another way, for different architectures, and we can have different implementation for the same ISA as well. And the thing is, right, so ISA is the set of instructions. This is the dictionary of the instructions that the CPU understands. And those who are taking the OS course with me, we said that one of the reasons to kill a process, to terminate a process, was the fact that it's trying to execute something that the CPU does not understand. It's an invalid instruction. So if an instruction is not supported in the ISA, it's not there in the ISA, well, the CPU will not understand what we are asking it to do, and hence the OS will terminate it, for instance, right? So this makes sense. This is the dictionary of the instructions that the CPU understands, so it's supported by the CPU. And then the market architecture could be seen as the implementation of the ISA, and we can see that we have different implementations for a particular ISA, and the whole, it's a bunch. It could be seen as a bunch of concepts dealing of the how the ISA is implemented, and now how the ISA is designed. So for the first part of this particular course, we're going to tackle the ISA, how to create the ISA, and how is the ISA is designed and created, and then we're going to move to the actual implementation of the ISA, and hence to the microarchitecture part, where we can have different implementation of the same thing. And the concepts, well, they include pipelining, branch prediction, out of order execution, etc., etc. And you have so many things that we'll be tackling in the microprocessor course next year. It's not going to be with me normally. For this year, we're going to just focus on one simple implementation, and then one a little bit more complicated but faster one. We're going to talk about those later on. All right. So this is where I wrapped up my face-to-face lecture, and we're gonna take it from there. Take it from here next time.